Alright, hell yeah. So here's our problem, and it's pretty cool. So we have a rigid body, we have 3 supports, we have this known load on a frictionless pulley, and so we know the tension in this rope. It's going to be L, even though it's faced that way, and, you know what I mean, we have L down this way and L down that way, so you kind of double up the load on that corner. And so we have... These are rigid, but they're pinned connections, so they can only take tension or compression. First thing we're going to do is just make them all in tension, because that's kind of like the answer. If these are going to be positive numbers, that's going to indicate tension. If these are negative numbers, that's going to indicate compression. And we're going to solve, which one are we going to solve for? Now we're going to solve for, I totally forget. I think we're going to solve for S3 in this one. So this is going to be pretty cool. Alright, so we're going to do the method where these, whether these are in tension or compression, they're forces and they have a line of action, and the line of action is going to meet, let's say, at that point. So if I sum the moments about that point, these forces have no distance away from that point. So the sum of the moments of these forces is 0. So the only other force, or forces that can cause moments, are this one, which is unknown. That's the only unknown force that can cause moments, and we're going to have a perpendicular distance over to this. Now this one's going to be fairly simple, but we might walk through some of the dot products to figure out how to use dot product to get a horizontal distance. And even though this one is just going to be spelled out for us, if we can find the intersection of this point, like some coordinates, well, we for sure know that this is a distance over of whatever, and we'll know that perpendicular distance. Because this is a vertical line, we're working with an XY coordinate system. So for all these, I've just chosen this point B to be 0, 0 because it's kind of the lowest and it's in the farthest left-hand corner. So I can say this is the positive Y direction, this is the positive X. That made the most sense for me. The other thing, instead of millimeters, we're going to say, hey, we're going to change this to meters. So this is 3 meters, 2, 5 meters, and so forth. Now this is 2,500 millimeters. That's going to be 2.5 meters. Because we have an answer as a fraction, I'm going to change this to 5/2. So that's going to be very helpful just to stay in fractions, stay away from decimals. Alright, hell yeah. And then we're going to bust out a ruler, and we're just going to make sure we get some lines going. So we have S1 and S2. Those are the ones... I can't see anything. Alright, good enough. Oh, yeah, good enough. Alright, and then S3 going all the way up. Cool, so this is the point. I did D for this one, E for this one. We'll say this is point F. And point F is going to have a, once we sum the moments, we're going to have S3 or unknown. We're going to have a perpendicular distance over to S3. That's the only thing that generates moment. I mean, you could have any distance over, but then you'll have to take the cross product. And the cross product is only concerned with the perpendicular distance. So we have this perpendicular distance over to S3. If I knew that perpendicular distance, the sum of the moment equation, and we'll probably put it right down here, sum of the moment about point F is going to be 0. We're going to have that perpendicular distance times S3. So whatever that perpendicular distance is times S3, and that's going to be a negative moment. And then we're going to have these forces over here, which are also negative moments. So our equation is going to be negative whatever that distance is minus whatever this vertical distance is to this force. We're going to have a component in that direction. This load L is at a 45, so it's going to have a component that way, and it's going to have a component down. And then this L will just be straight down, but it'll also be a load L. Okay, so that's kind of the foreshadow of what we're going to do. First, we need to know where the location of these 2 points meet. So we need an equation for, basically just an equation for 2 lines. So here's our equations. And so this is our coordinate system 0, 0. So let's start with S2. That's probably the easiest one. And we have the general form of an equation is y is equal to mx plus b. we don't have any y-intercept right here. And this slope is 1. So we have 1, 1, 45-degree angle. So the equation for this line is y is equal to x. That was pretty simple. Now up here, this is going to have a distance of 5 halves. So our y-intercept is going to be 5 halves. And I don't know, sometimes it might be easier just to write the equation of stuff you know first. I'm going to say y is equal to, let's just do this y-intercept first since I know that's 5 halves. And now we need to figure out what the slope is. And the slope is going to be based on geometry. This is down 1 over 2. So that's going to be the geometry right here. 1, 2. And that's the slope. It's going to be down 1, negative 1 over 2. So we're going to have a slope of negative 1/2 x. When these two equations are equal to each other, so I'm going to substitute, and it's kind of funky, but so y is equal to x, and I have a y right here. So I'm going to substitute, I'm going to say x, so this is the x. So we have x, 5 halves, and I could say, I could say x of S2 right here, and then this is y of S2. But, you know what I mean? And sometimes, oh man, I really do. But yeah, hopefully that's just enough to like wet your whistle. But basically, because the intersection of these two lines is where I have an xy coordinate system for this S2, and that's going to have to equal the xy coordinate of S1. So if I say this is y of S2 and this is x of S2, and I say this is y of S1 and this is x of S1, well, I'm saying the other two equations, yeah, this will be kind of cool. The other two equations would say that ys1 is equal to ys2 and xs1 is equal to xs2. So that's kind of the unsaid thing when I say, hey, I'm just going to take this this equation and shove it right into there, so this y just becomes x. That is spelling it out. So I have x is equal to 5 halves minus 1/2 x. Now I need to solve for x. I'm going to add a half to the other side. I can say this is 2 halves. So 1/2 plus 2 halves is 3 halves over there. So we have 3 halves x is equal to 5 halves. Take the 2 upstairs. Those are going to cancel 3 downstairs. So x is going to be 5/3. So this was, that fraction is not nice, but it is a fraction. And so, and what's our y? Well, x is equal to y. So our y is also going to be 5/3. And now we have our coordinate system. 5/3, 5/3. So let's write that in. So we have the coordinate of this is 5/3, 5/3. Okay, and we know the x-coordinate system of S3. It's over 3. So what's our horizontal distance? The x component here is 5/3, and this is going to be 3. So our horizontal distance, I'm just going to do this perpendicular distance, but I can say f prime right here. So the distance f prime is going to be the x value of this is just going to be 3 minus 5/3, which is 9/3 minus 5/3, which is 4/3. But now we're going to take about 5 minutes probably and figure out, could we have done this with the dot product? Like, how do we do it? I mean, it's just, let's do it then. All right, so I'm going to say, what am I going to say? We need if I'm finding this, if I'm trying to find this perpendicular distance, I know it's a component of a right triangle, so that's one way. And if I'm saying I want to use the dot product, which is usually a cosine, if you have a vector, let's say this vector is, like whatever. You have a vector that's 3 units long, that's what I used for the last video, and then you're going to dot it, you need to dot it with a vector that's 1 unit long. And that vector is going to be at some sort of angle, so you're only going to get a percentage of it. Kind of like the cosine components, the shadow component of the vector. But anyway, so what vector would we even want to use? I need to pause the video for that. All right, hell yeah, we're going to do this 2 ways, so we'll probably have to kind of write small. Because maybe this is a hypotenuse, and if I knew this hypotenuse, I could use the dot product to find that component. Also, this is a hypotenuse. So maybe I'll do one and then the other. Alright, so I do need to know the coordinate system of where S1 meets S3. And so we have to do that. S1 is this equation, and S3 is x is equal to 3. So I'm going to have 5 halves minus 3 halves, and that's going to give me y is equal to 1. Cool. So right here I know that y is equal to 1, and x is always equal to 3. So that's the equation for that one right there. Now I need to know the equation for this one. We have S2 is equal to y is equal to x, and then S3 is x is equal to 3. You know what I mean? So, and again, using this equation, well, the x's and y's for both these equations have to be the same. So this 3 has to be that 3, and y is equal to 3. So that was pretty easy. 3, 3 is my coordinates up here. And now I have to use vectors. Let's see. How would I do this? Alright, yeah, this is such a good practice for me, because this is definitely not... I want to know... I'm going to say this is FG now. So this is the vector FG. And if I knew the vector FG, if I knew like the I component, the J component, then I could dot it with a unit vector along this axis. No, I'm sorry. I would dot it with a unit vector along the perpendicular distance that I'm trying to find. So if I do that, that would give me the perpendicular distance. So, yeah, and I'm doing this more for me, just so I can actually run through the words of what the dot product is. If I know, if I have the coordinates for a hypotenuse, then I can dot it with a vector in the one of the cosine directions. Or, if this is a hypotenuse and it's part of a right triangle, hell yeah. And if I want to find that length of that side of that right triangle, then I need to know a vector along this this side of this triangle, and I want to take the unit vector of it. And so if I dot this vector with the unit vector of that, that's going to give me that component. And this is a hell of a lot of work just to make something real simple. But the other thing that I'm not very good at is like, hey, so we have two vectors, or need to slow down. What is the vector VG? Well, the vector, and I'm going to say this is B right here, so we have B. So the vector, the vector FG is going to be, how do you even do this? Sometimes I need to, like, is that going to be BG minus BF? Because if I did BG and then plus BF, I would be going this direction. I would go BG, and then here's BF, but I got to do it this direction. You know what I mean? So we're kind of using that parallelogram method. But if I go BG minus BF, then I'm coming back here. And still it doesn't look like it's BF. But here, I'll do this, and you're like, oh, then it kind of does. But instead of going BG minus BF, let's go... well, let's start up here and then go BG minus BF. You know what I mean? So there you go. So you have kind of two different. So I definitely have BG minus BF is going to be this vector. If I'm starting here, going BG minus BF, here's the starting point, and so here's my resultant vector. And that vector is identical to FG. It's just not in that same location, and that trips me out. But that's why I hate. I would just rather have the coordinates. Hey, I'm at F. How the hell do I get to G? Well, I have to go. It looks like I got to go that way, and then I got to go down. And it's just the difference between 3 minus 5/3, which we just said was 9/3 minus 5. So that's going to be 4/3 this way. I'm going to write that in. 4/3. and then I'm going to have 5/3, and then I'm going to have, then I got to go down 1. That's going to be 1 minus 5/3. All right, so, but let's do that from, like, the technical perspective of FG. Vector FG is BG, and BG is, BG also is just 3 minus 0, 1 minus 0. But because we have an origin of 0, I'm going to have, that's going to be BG, which is 3i plus 1j. And we're going to subtract, make sure to get parentheses on this, because we're going to subtract BF. So FG is, I should have wrote this, it's BG minus BF. Alright, and BF is 5/3 I plus 5/3 J. So now let's, we're going to say this is 9/3 and this is 3/3. So 9/3 minus 5/3. That's going to be 4/3 I. Now we have 3/3 minus 5/3. So that's going to be negative 2/3 J. Okay, hell yeah. So we finally got vector FG. That's a hypotenuse. Now we want to dot it with a unit vector along this this component direction. So, and this component direction is perpendicular to maybe S3. Maybe we know S3, and we know that its slope is over 0. Its slope is would I run into an issue there if I had to say the slope was infinite? But thank God we don't, because we just need a unit vector in this direction. And it wouldn't matter anyway because so yeah, we have a horizontal and we have 0 slope. So oh yeah, that is tripping me out, because if I have any sort of slope, how I would do it would be like, yeah, down 1 over 2. This isn't a unit vector because this is the square root of 5. I would have to get this in terms of like 1 divided by the square root of 5, and then 2 divided by the square root of 5, and now this is a unit vector of 1. But yeah, just by observation, like this is a this has no component in the j, it's all in the I hat component. So a unit vector is just going to be 1 I hat. Alright, so hell yeah, so we want to know this perpendicular distance f to f prime. So it's a vector, but I'm going to do absolute value. That's how we say the magnitude. And the magnitude of that is the vector fg, which is a vector, but we're going to dot product with the unit vector, which is, one way to write it is just the vector fg, or f to f prime. The absolute, it's just that vector divided by the absolute value, f to f prime. Oof. But yeah, this is misleading because it's basically, how it's written right here is it's saying that I know this vector from f to f prime. That's what I'm trying to actually find out, like both these. But I just know a unit vector is going to be positive 1i in that direction. So hell yeah. So we're going to have 4/3 I minus 2/3 j dotted with, 1 I hat. And then maybe you could even do plus 0 j hat just so when you do the dot product, you're going to multiply like terms. 4/3 times 1 is 4/3. And then you're going to, so yeah, let's do it 100%. So we got 4/3 times 1, and now you're going to add it to this, which is negative 2/3 times 0. That's the j components multiplied. That's 0, so that goes away. And our result is 4/3, which is that perpendicular distance. So just a long way to go for something that was just very, very easy to see by observation. Alright, so instead of taking the vector, because because now for the next one, I'm going to say this is my hypotenuse, and G, F, G, H. So I'll say this is H up here. But instead of saying this vector from F to H is going to be B to H minus B to F. That would make sense. If I go from there, if I go all the way to there minus this part, ooh, that's actually in a linear way that really represents for sure, then that's going to be that vector. But if I just want vector FH, so let's do this. So we have FH, and maybe we can do this all in one go. What are we trying to find? Well, we're still trying to find the absolute value of this vector, let's say, that horizontal, this perpendicular distance is going to be the vector FH dotted with the unit vector in that direction. So I'm not going to even rewrite this because that's misleading, because we didn't even know, we just knew what the unit vector was. So I think there's a better way to write unit vector. I think you do maybe like this lambda sign. But anyway, so but yeah, the unit vector in that direction is just a positive 1 I hat. Alright, and vector FH, that's going to be the I component, so we're going to have 3 minus 5/3 I hat plus 3 minus 5/3 J hat. Cool. And we said this was 9/3 minus 5/3, so we're going to have, and we still got to dot it with 1 I. So we're going to have 4/3 I plus 4/3 J, and that's what we see, dotted with 1 I hat. Okay, so again, we still have 0 J hat, so we're going to have 4/3 plus 4/3 times 0. So this gives us that same answer of 4/3. But I find it fascinating to take something that's just super obvious. This perpendicular distance is just the difference between the coordinates, between 3 and 5/3. That's going to be that 4/3. But just setting up this hypotenuse and then dotting it into a unit vector in that direction gives us that perpendicular distance, and it just shows you. And it shows you what cancels out as well. So I think that was useful. Anyway, yeah, since we're doing this problem 3 different ways, because from here on out, it's kind of all the same. Now we know that perpendicular distance is 4/3, so we can go back to our sum of the moment equations about F, about where these two vectors, their line of action meet. So when we sum the moments, these vectors don't have any distance away from that point. So these don't generate any moment. This one does. S3 is that perpendicular distance. It's 4/3 away. We're going to generate a negative moment. That's what that is. And we need to know what S3 is. Okay. And then this tension in this rope is 2 different ways. It has a component that way, a component that way, and another component L down. All right, so we need to know this distance from here to here. And yeah, again, we could also do this. Like, let's say, because I just know that this coordinate right here, well, it's up a little bit. You know what I mean? It's this coordinate is 5, 1/2. And so the vertical distance is, because this is my y component, this is my y component. So the vertical distance is 5/3. Let me write this up here. 5/3 minus 1/2. So that's going to be the vertical distance. To add or subtract these vectors, I need the denominators to be the same. So this is going to be 10/6 minus, if I break this up to 6, this has to be 3/6. 3/6 is the same as 1/2. So 10/6 minus 3/6, this is going to be 7/6. But hell yeah, I'm sorry this is such a tiny drawing. It should be a little bit bigger for this video. But we're gonna do that same process and be like, well, couldn't I have found this vertical distance by using the dot product? Hell yeah. Because I'm going to say now, well, we got F, G, H. I'm going to say this is this is point I. And now I'm going to say I have a vector Fi. And I'm going to dot it with a unit vector in this direction. So let's draw this in. So I have Fi. This is my vector. This is my hypotenuse. And what I want to know is this distance. Cool. And so we're going to do this twice. Because if I know Fi, and I dot it with a unit vector in this direction, which is going to be and if I'm starting at F and going this way, then I want to dot it with a unit vector from here to there. So that's going to be a negative j. So a negative 1j is what I'm going to be dotting it with. That's going to give me this distance. But also, we have two different things here. I can take Fi, and then, so it's this, and then I can dot it with, hey, a unit vector along this path, which is going to be a positive 1. Positive 1I. This dot product is going to give me this this distance from here to there. The distance in the x to this to this axis. All right, let's figure out what Fi is. So Fi, and again, like I hate doing. So what would Fi be? Fi would be Bi minus Bf. Because if I go Bi and then subtract Bf, that's the parallelogram that I'm making. And would that make sense? Because if I start up at F and I go, so I went Bi, so if I start at F and go that same direction, Bi, and then minus B, oh man, did I even do that right? But yeah, Bi, Bf. So if I start here and go Bi minus Bf, hell yeah, I get to this point. And that would be Fi. Oh, but I hate that method. So I just like to say, hey, what's Fi? Well, start at your farthest point and subtract this point. So that's going to be 5 minus 5/3. This is going to be my x component. And then I'm going to have 1/2 minus 5/3. Cool. So this is going to be 15/3 minus 5/3. So that's going to be 10/3. So my component, so Fi is going to be 10/3 in the I direction. And then I'm going to have 1/2 minus 5/3. Can't do that. That's going to be, 3/6 minus 10/6. So this is going to be negative 7/6. And so I'm going to have a negative 7/6 j component. Cool. I'm going to dot that with negative 1j. All right, hell yeah. So the I component, this is a 0i, so 10/3 times 0, 0, and then plus negative 7/6 times negative 1 is basically 7/6. And that's going to be that distance. Sorry, this distance. This is going to be 7/6 in this direction. Now this distance, well, that's going to be that 10. I mean, we just did it twice, but doing the dot product, you're going to have 10/3 I minus 7/6j dotted with 1i. So now we're going to have 10/3 times 1. That's going to be 10/3. And then plus negative 7/6 times 0, because this is 0j. Cool. So then you're going to get 10/3. That's going to be this distance. So we have this distance, 10/3, and this distance, 7/6. All right, booyah. So now let's use those. So we're going to have our moments about F. We already did that perpendicular 4/3 to S3. That was going to be a negative moment. We're going to go this distance. Now we're going to go this vertical. I do this one down first. So we're going to go down 7/6. It's this is where my fingers are. I'm going to start at F. Fingers in the direction. Direction of this 7/6, and then sweep my fingers in the direction of this tension force. This 45 has a component that way and this way. This is the one that I'm multiplying. So 7/6 multiplied by L, but it's this component's a 45, so it's only 1 divided by the square root of 2L. That's that component. All right, so now the other two are distances of 10/3 away. So we're going to, and they're also a negative moment. So we have negative 10/3, 1 divided by the square root of 2L minus, and then we just have a full L. 10/3 is the distance, and the full L. That's going to be equal to 0. Okay, hell yeah. So now to solve for S3, these are all negative, but everything's negative. So to get S3 positive, I would have to take this to the other side. And that's going to give me a positive S3. Now I'm going to, like juggling, I'm going to do a few things at once. I'm just going to pretend like this is already over there, and it's already a positive, so that goes away. And now these are still negative. All three of these are. But now I need to divide all of these by 4/3. Dividing each of these by 4/3 is the same thing as multiplying by the reciprocal. So I'm going to multiply these by 3/4. So I'm going to have 3/4 times 7/6. Also divided by the square root of 2. But 3/4 times 10/3. So let's do that. So 3/4, so I'm going to have 7 times 3, 6 times 4. So I'm going to have 21, and still the negative though. I always forget to do that. So 21 divided by 4 times 6 is 24. I'm going to have the square root of 2L. Now I'm going to have 10 times 3. That's going to be 30. All right, home stretch. Okay, so we have 10 times 3. So I'm taking this 3 and then getting it to the other side of the equation. Pretend like this is almost, anyway. We're doing a couple steps at once just because I can do this whole problem just with this sheet of paper. So it's kind of cool. Anyway, so 10 times 3 is 30. 3 times 4 is 12. Square roots of 2L. Same thing here. 30, 12. There is no square root of 2. It's just 30 twelfths L. Hell yeah, this is what S3 is. S3 is equal to this. I don't have to rationalize the denominators yet. It doesn't matter if I have the square root of 2 in the denominator. These both have square root of 2 in the denominator. So if I get these two denominators the same, just by multiplying this by 2 and this times 2, then I have 24, and then I can add those up. I didn't do it that way because I already knew what I was going for. But let's try that. So we're going to go S3. This is going to be 60. And we're going to have negative 60 minus 21. That's going to be negative 81. Negative 81 divided by 24 square roots of 2 minus 30 twelfths. This is an L there, and then L there. So how do we simplify this? Because 24 is divisible by 2, 81 isn't. So is it the next number to see if it's divisible is 3. 3 times something equals 24? Hell yeah. This is going to be 3 times 8. Does 3 times something equal 81? Well, what is 81? You know what I mean? Well, that'd be a 9 times 9. Oh, yeah. So that's going to be 9 times 3 times 3. So, booyah. And so this is going to be 27 times 3. So, yes, I can factor out a 3 right here, and I would get something... yeah, and then this would be 8. So yeah, let's just do that one step at a time and see if we get anywhere close to what we want. So we're going to have negative 27 divided by 8 square roots 2 minus. But now here, this is a 12. So the denominator isn't 8. So now what do I do? You know what I mean? Could I... yeah, and I don't think this is... Yeah, well, what are the strategies to find lowest common denominator? I'm not quite sure. But this took me a while anyway. And I don't even know another way to do this. I just know that, yeah, it was useful to divide this by 3. So I said this was 10 times 3. And this was 12. And this was 4 times 3. So this was going to be And even just to do that much, so we're going to have 10 force L. And then right here it was like, oh, then it was a little more obvious. Oh, did I even do that right? Oh, holy hell. No. Since I'm trying to go for this answer in the end, this is where I have to rationalize my denominator. So even before doing this, we should have rationalized the denominator just to see where we're at. Okay, so multiply top and bottom by square root of 2. Now we're going to have S3 is negative 27 square root 2 divided by 8 times 2. This is going to be 16. Cool. And this can't be any lower than 16. So now I'm going to subtract 10 fourths. But now I can turn this in, I can say multiply top and bottom by 4. So I'm going to do 40 sixteenths L. So now I can put these together. Since the denominators are the same, I can say S3. And what are we going to factor out? We have a negative on both of them. So I'm going to put the negative right at the midpoint of the quotient. So negative 27 square root 2 plus 40 divided by 16. And then put the L out here also right at the midpoint of the quotient. So then, I don't have to put parentheses around that. That's implied. But hell yeah. So now we have S3 is 27 square root 2 plus 40 divided by 16. But these problems are fascinating because, you don't know you have the right answer. I mean, just like every problem, but, you don't even know if you're approaching the right answer. Because, especially on this one, it seemed like everything kind of came together in the end. But yeah, I remember that. Rationalizing. For these problems, it was way simpler to not rationalize. To say that if I was adding these, you can just factor out that 1 divided by the square root of 2. You know what I mean? Get it outside into the outside, and then this is just going to be negative 7/6 minus 10 thirds. You know what I mean? And then you could even go one step further, and then we'll end the video. Because if I'm actually doing these, this is going to be which we didn't. I mean, I guess we didn't do it till a later step, but to add these two straight across, I'm going to have, this is going to be negative 7/6 minus 26. Cool, so that's what I'm going to have. But even right there, instead of treating these like fractions that you're adding, what I like to do is just, pretend like this is just negative 7 minus 20. And that's the same thing as just getting the 1/6 the hell out of there. You know what I mean? So we're going to have 1/6 square root 2. Get that out of there. And now you just have negative 7 minus 20. So that is literally the juice that you're adding. Negative 7 minus 20, that's going to be your negative 27. And then even from that perspective, it's just like, oh, yeah, we were a little bit closer. Had we have done that, then you're a little more on point maybe to getting that answer. Instead of what we did. Alright, sweet. Anyway, heck yeah, so we got the answer for S3. What did we do? We kind of doubled down on what the dot product is. The dot product is, hey, I have a hypotenuse, and I know the vector of that hypotenuse. What I want to do is find a component of that right triangle. And I think I'm definitely going to end with this. So this shows that if I have any sort of let's say this is my hypotenuse. It looks like, just from the way I drew it, it looks like, and this is where I'm totally going to break out a sheet of paper. Oh, hell yeah. So I have these little cards. This is such a cool tool just to have a little card out here. Because how I drew this, it totally looks like, you were suspecting that I was drawing this triangle just like that. Just the way I threw the hypotenuse on the page. Like, hell yeah, those are its components. And we said if I know this vector, I can dot product into a unit vector along this. and the way I have it drawn, maybe this unit vector is in the j direction. It doesn't matter if you said it was negative 1j or positive 1j. As long as you're just trying to get an absolute value for a distance, you can just, if you get a negative, just know to take the absolute value of it. Okay, but the take-home point is, just because I drew the vector like that, and let's draw another line, just to compare, for sure does not mean that I'm trying to find just these two components. What I can do with my card, I can take this any direction I want. I can take it way up here and say, hey, I want to know the dot product. I want to know this dimension. Okay, cool. Let's say this is a 1, 1 line, and then so I'm starting, this vector is like AB, and this is going to be my B prime. Cool. So I want to know this dimension and how I would say that. And if I'm starting here going there, I kind of want to know this this dimension. And so I would say it's B prime to B. It's that vector divided by its magnitude. B prime to B. So this is the unit vector in that direction. But if I already know by geometry something about that direction, which I have 1, 1, and then 1 squared plus 1 squared, this hypotenuse would be the square root of 2. But again, this is not a unit vector. I would have to divide all sides by the square root of 2, so that's kind of using that property. And I could have done that right off the bat. Once you get used to it, you could either just know 1, 1, square root 2, just know that your unit vector is 1 divided by the square root of 2. It's not rationalized, so then you might want to know this is square root of 2 divided by 2, because you would have to multiply top and bottom by the square root of 2, and then this would be square root of 2 divided by 2. But, you know what I mean, whatever. But at least we know that's going to be our unit vector. So if this is a 30-degree angle, and my vector AB is a square root of 3 divided by 2i, that's a 30-degree angle, and then plus 1/2 j. I'm going to dot that with a unit vector over here, and so that unit vector is going to be, the I component is going to be 1 square root 2, I plus, minus 1 divided by the square root of 2j. And then if I dotted this, that would give me that perpendicular distance right there. And yeah, I mean, let's do it in our calculator just to see. Yeah, if I have a 30-degree angle, and then I'm coming in with a 45, what's this vector dotted with that? I'm just kind of curious. So we have square root of 3 divided by 2. That's going to be the I component. And oh, I shouldn't be using calculators because we'll probably be able to get this as a term, you know, we'll get it in terms of square root. So I'm going to have square root of 3 divided by 2 multiplied by 1 square root of 2. So I'm just going to have that. And then we're going to add it to 1/2 times negative. So I'm just going to subtract 1 divided by 2 square roots 2. Oh, hell yeah. So the denominators are the same. So I can say that this is going to be the square root of 3 minus 1. Well, I should probably rationalize before I do that. So let's rationalize, and I'm going to multiply top and bottom by the square root of 2. So this is going to be 4 on the bottom, 4 on the bottom. So now I'm going to have a square root 2, and then on both, so I'm going to have square root 3 minus 1 divided by 4. So hell yeah, and that's exactly what some of these solutions were doing, and that was going to be that distance. Now, just say, like, let's say AB is 1, divide this in 2. This better be somewhere close to 1/2, but probably more. I bet you it's like 0.6. Okay, so let's double check reality. Square root 2, square root 3 minus 1, minus 1 divided by 4. Oh, why the hell were we so off? Alright, we're just bleeding time, so let's find some errors, because I don't trust that that answer was right, and I don't know why we munched it. Alright, so we got a square root 3 divided by 2, and we're going to multiply that by 1 divided by the square root of 2. Okay, and now we're going to add it to this next term, 0.5, times negative 1 divided by the square root of 2. And we get 0.25. Do I just have it drawn wrong? I'm losing my mind here. Alright, hell yeah. So let's do this 30-degree triangle. That's going to be 8, 6, 6. So I got 8, 6, 6. So that's right there to there. And then we're going to go up 5, or up a half. Alright, hell yeah. And that means that this should be a full 1. So that's going to be 10 centimeters. And yeah, we're pretty good there. And then we're going to, yes, that's pretty accurate. Almost right there. And then so we're going to be, this is going to be our 45. Alright, sorry about that. So, hell yeah. So we got our 45. Yeah, it's just kind of weirded me out that, be just a little bit lower. Alright, sweet. So there's our 45. Here's our vector. This is our vector AB. Whoops. And we want to know the perpendicular distance. Yeah, I just had it drawn just real bad. So yes, the perpendicular distance, and I should have a square, is going to be, well, I mean, we just solved for it. It's going to be 0.258. Yeah, so I just had it drawn wrong. So 0.258. And hell yeah. So now that is going to be the perpendicular. So this distance right there is 0.258. And we can do the other. We can figure out what this distance is, because this is going to have a 1 square root 2. So let's do that. So this distance we want to know. And so that's going to be distance AB, the absolute value of vector AB prime, is going to be AB dotted with a unit vector along here. And wait, what did I? Yeah, this is this gonna. We said that, yeah, this is gonna be a 1, 1. Yeah, so from here I see that, yeah, that is drawn wrong. This is a little bit steep. This is for sure steeper. And the other thing to do, even with, yeah, I guess I'll just take a sheet of paper. You know, just take a sheet of paper and fold it with a 45 and just see, is that even a 45? Oh, hell no. You know what I mean? So our 45 was way off. Our 30-degree angle is probably pretty bad too. Cool. And even just coming in here with a sheet of paper to getting your perpendicular, just take it to that point. And so here's going to be that perpendicular distance. And if this is a value of 1, half is going to be right there. And then so this 30-degree triangle should be way the hell up there. So that also shows that that triangle's got to be way up there. So there you go. So yeah, so I was way off. So a 30-degree triangle is more like that. Is that right? Man, that's wild. Because if that's 1, the halfway point is going to be right there. Oh yeah, so I'm drawing 30-degree. When I'm drawing triangles, I'm saying like that's a 30-degree triangle, and that's just horribly off. So The other thing to do is like a 90, come out here, and then divvy this up 3 ways. And that is a 30-degree triangle. So yes, that's way taller or more angled than I typically draw a 30-degree triangle. Okay, so let's finish this off. Let's find that distance. So we need to take AB, which we have. It's the square root of 3 divided by 2I plus 1/2 j. And we're going to dot it with a unit vector in that direction. And so I'm just going to say, and a unit vector in that direction from a symbolic perspective is vector AB, if you knew it, divided by the absolute value of the vector AB prime. So it's vector AB prime divided by itself. So if this was, anyway, all right, let's get on with life and call this video. So we have square root of 3 divided by 2I plus 1/2 j. That's this vector AB. Dotted with the unit vector, I just know it. It's going to be over 1 divided by the square root of 2I, and then up plus 1 divided by the square root of 2j. Alright, so like terms multiply. We're going to have the square root of 3 divided by 2 square root 2, multiplying these, plus 1 divided by 2 square root 2. Okay, sweet. So this is just going to be square root 3 divided by 2 square root 2. And rationalized, that's going to be square root 3 square root 2 divided by 4. And hopefully that's right. I'm going to store this as alpha A. And then we're going to go square root 3 square root 2 divided by 4, stored as alpha b. Because now alpha a squared plus alpha b squared, square root of that, should be ab. And yeah, so we messed up just a little bit on that. We have vector ab. We're right on that, and we're dotting it with a unit vector in this direction. We're going to go over 1 divided by the square root of 2, and then up 1 divided by the square root of 2. Yep, and so we're going to have square root of 3, 2 square roots 2, plus 1 divided by 2 square roots 2. Oh, yeah, I don't know what the hell I was thinking. Sorry about that. This, you can't add, like, sure, these are the same, but like this is oranges and this is just numbers. So yeah, you can't add those. So yeah, let's rationalize. Multiply top and bottom by the square root of 2. And this now becomes the square root of 3 square root of 2 divided by 4. But this, I don't know what I was thinking. But yeah, this becomes the square root of 2 divided by 4. Cool. So our final answer is square root of 2, square root of 3 plus 1 divided by 4. Hell yeah. Square root of 2. And this is very similar to the problems we're doing to kind of simplify these. So this is just good extra work to do. So we have square root of 2, parentheses, square root 3 plus 1 divided by 4. Hell yeah. And that was the one, like back here, it's nice to do stuff graphically because you're like, hell yeah, this is, like, I know what the length is. This is a check on reality. I don't know why I don't do this first and just know, like, hey, this has to be 0.96. And it is. It's 0.965. Store that as b. So now the square root of a squared plus square root of b squared. Another check on reality. That's going to be equal to 1. Sweet. So we did it. Yeah, I've been having a lot of fun with this problem. Just the fact that you have 3 vectors kind of coming together. If you take the line of action of 2 of them, then you can take those coordinates, find the perpendicular distance to the other one. You can sum the moments, and you get just one equation. One equation, one unknown, and then so it was very easy to get these answers, especially since they were in fractional form with a lot of irrational numbers. Alright, so thanks for joining me, and guess what? That's a video.